So we do all the parent functions in chapter 3, right? And the reason we have a specific section for rational functions because they come up quite frequently and they have a few of the finer points that we need to address. Okay, so the parent function is 1 over x. Try to cycle that in your memory what it looks like on a graph. You remember. Something like that. If you just sketch it, it would go right like that. Can you describe the end behavior? Y approaches. Where does this graph go? The y value. The x goes to infinity. But the y value, where is it headed? 0. Towards 0, right? Okay. And as x, then we have to do both sides. Approaches negative infinity, y approaches 0 again. Still. Okay. That, like I was saying earlier, if you get a number right here, this function has a horizontal asymptote. Right there. Okay, and it's the line, the equation of that horizontal asymptote is y equals 0. Just a horizontal line, right? Okay. Really serenaded. You shut that door.
Yeah.
Just prop it. Thank you. Alright, we also can, M asymptote. It's kind of a funny word. We can also have, what might you call this?
Vertical.
Yeah, vertical asymptote. I'm curious as to where that word came from actually now. What's the equation of that line? In this case it is x equals 0. Algebraically, can you see why that graph does not cross the x-axis or the y-axis? You look at the function. What's the problem? Yeah, what number can't be in the denominator? 0, right? So you're completely, when you're doing a vertical asymptote, okay, where is the denominator? Equal to 0. That's your question you need to ask. There's one special case where there's an exception I'll show you. Okay, but asking that question is how you find the vertical asymptote. And then of course the horizontal asymptote is in behavior. So. Okay. I'll show you some situations where those come about. And some more difficult rational functions where we have to calculate those values. Good? Just definitions. All right. Okay. Let's look at some rational functions. And you want an easy one first? I put it in parent function format, so that makes things a lot easier. Do you want me to graph it first, or can you identify it right off the bat? Just identify those asymptotes.
Graph it.
What movements do we have?
To the left.
To the right.
To the right, I actually.
Yeah, it's the right too. Remember, left and right because we're paired with the x, and it's opposite of what it says. So, right 2, and up 3. So, you just want to kind of give yourself some guidelines. You're just moving that parent function as such. Like that.
Oh.
Right to it. Pretty basic. Okay, so can you identify the asymptotes now? Are you okay with HA, horizontal asymptote? You can follow that. Okay, what's the equation of a horizontal asymptote?
Y equals 3.
Yeah, we're 3 up, right? Y equals 3. And the vertical?
2.
Okay. There you go. So, parent function format makes that super easy. Of course, not all things are super easy in math, right? Of course. If you don't want to graph that, you don't have to. What makes the denominator 0? 2. That's your vertical asymptote, right? And then what makes a plus 3? Moves up 3. That's your horizontal asymptote. So algebraically, you can just look at that parent function formatted equation and get your answers. Okay. If you need to graph it, have at it, but you don't have to in that case. Okay. Yeah? Okay. Let's look at one that's a little bit more intelligent. And there you go. Vertical asymptotes are usually pretty straightforward. What do you got?
We're not too different.
Remember, vertical asymptote, what's the question you're asking? Where's the denominator? 0. So, so we have x equals 2. Right there. 2 minus 2 is 0. Right? horizontal asymptotes in this case are more difficult because that's not formatted as a parent function, child function. Here's the best method that I've found. We're going to divide all terms by the highest exponent of x. In our case, what's the highest exponent?
3, 2.
The highest exponent. That's the highest coefficient. Yeah, the highest exponent in our case is 1, right? So in this case, x to the first, right? So we're going to divide every single one of these by x. Okay, so that's x to the first is our highest, so simplify that algebraically. What's 3x over x? 3 minus and 1 minus 2 over x. Are you okay with that? It's something you've probably never seen before. You're like, what the heck is going on here?
Yeah.
So this is just a method to calculate where the horizontal asymptote is. Okay.
Is there another method?
Yeah,
Can you see those?
sure. I'll show you the other way. Okay, so you've divided by the highest exponent of x, simplified. The horizontal asymptote is y equals 3. So just the two numbers that result, if there are two numbers, y equals 3. 3 over 1, right? Why don't these matter? Okay, you think end behavior. If x is approaching infinity, what is that going to close to? 0, right? So these basically eliminate themselves. In the end behavior argument, it's the same thinking. This is one way to find end behavior. Okay. It's called an infinite limit calculus language. So yeah, as x approaches infinity, this gets really close to 0. So we can eliminate this. That's one method. Do you want to know the other one?
Yes.
Okay. I think it is solve for x. That's a 1, isn't it? So this is an algebra problem. Solve for x. These can get a little messy, but if you multiply both sides by x minus 2, these are eliminated, right? There's some ones. So what do you think you want to do next?
After one.
That's definitely going to cause us problems.
Divide by 3.
Divide by
3.
Already?
So divide by 1.
Divide by 1 is just on the other side.
So there are lots of ways to do this. We want, since the y is still multiplied by something, we still want to keep these in chunks. Okay. So we can do that several ways. One is to divide by 3x minus 1, and then divide by y. So here's one way. So we get what's left on the right side? Not 0, it's 1. When you eliminate those. And then divide by y. Or multiply by 1 over y, whatever suits you. So we get hold on a second. Something's not right here. My mind is telling me that something's not right. All I'm doing is solving for y now. I would have like autopilot. Okay.
Hold on.
So that's why we don't write in pen in math class.
Plus, I didn't, but I liked my reading.
Let's not go on autopilot. We're solving for x, right?
Yeah.
Okay.
So, no, we're solving for the fourth one class.
Distribute.
Oh. Hold on.
Well, I used that whole book of
Oh, did you like distribute? Yeah.
Yeah. The reason I prefer the other method is because it's a lot more simple in my personal opinion.
Yeah,
But,
this is confusing.
okay, so we distributed. Let's put all the x's on one side, and I'm going to move the y to the right side. So, you see what I did?
Yeah.
So I subtracted 3x from both sides, and I added 2y to both sides. So if you get the x's on the same side, what can I do with that phrase? Add?
You can divide y.
Not yet, because there's no y here, but I can factor an x out of both terms. And what that does is now I can divide by y minus 3. X equals 2y minus 1 over y minus 3. Stupid Hebrew tricks. What's the horizontal asymptote?
Y equals 3.
Wow.
What?
Again, ask the same question, where's the denominator 0?
Ah!
Okay. So you can use either method, I don't care.
That hurt my brain.
So that's an algebra, that's just a lot of algebra. Again, either one works, I don't care which one you use. I prefer the top because I know calculus, so there you go. Okay, so horizontal asymptotes can be a pain in the butt, right?
Yes.
I do want to show you one situation. So, we're a vertical asymptote. There's a special exception to that question, where do you divide by 0? Okay. So, let me give you a function. You look at that and I ask you, where are the vertical asymptotes, what would you say? At x equals 2, right? Okay. There's not a vertical asymptote at x equals 2 in this equation. Okay. You have, so if you can factor the bottom out, there's no vertical asymptote. It's actually a point discontinuity. Okay, so can you factor the top? Right? Remember how to factor quadratics. We're going to go over it in detail here in the next few weeks. Okay, so I factored the tops. Remember, you multiply to get -4. And then there's a 0x in here. So add to get 0, so you got 2 and -2. Okay, I can cancel these out, right? There's no vertical asymptote at x equals 2 in this equation.
Oh, we can find the
That's the
denominator.
special exception. There's a point discontinuity.
How does it look graph?
At x equals 2. What would the graph look like? Here's what's really neat about these. All you have to do is graph that function with a point discontinuity at x equals 2. Okay. So, yeah, you've eliminated, see, these cancel each other out everywhere in the graph. You're just graphing x plus 2, so then you have a hole at 2. That's the graph of that rational function. So special case. No vertical asymptote because we can factor the denominator out. In fact, if you could do that problem right there, you just did a free response on the AP Calculus test from Chapter 2. Yep, you just earned a couple points. Easy. Easy is a 4-letter word in some people's minds, my friend. Let me make sure we got nothing else going on here. Please say there's nothing else. Yeah, that's what I'm thinking. The book does address slant asymptotes. Don't worry about it.
Write down stuff for chapter.
Okay, so So the book does have slant asymptotes in there. Don't worry about that. And there are graphs that have two vertical asymptotes. Okay, so if you have two items in the denominator, you might have a vertical asymptote and another one, right? So, but it's again, just what is it, what makes it divided by zero, so. All right, I think we're good. We'll give you some time to practice, and if you get stuck, I can help you.